This is number 64 in chapter 10. It's looking at three-dimensional structure along with hybridization and bond types. The question asks us to write a hybridization and bonding scheme for each of the molecules. We want to sketch the structure. We will also want to indicate hybridization of the central element, as well as types of bonds about the central element. And so part A is looking at SO3 minus 2. And if we follow our electron count, we would expect to get a structure that has two sulfur oxygen single bonds, each one of those oxygens being negative, and then we end up with oxygen having the last oxygen having the double bond with the sulfur, which means sulfur still has a lone pair of electrons. If we look at that sulfur element, we see that it has four groups about it. So this would be a tetrahedral electronic geometry. And that sulfur would be that sulfur would be sp3 hybridized. In order to have that electronic geometry of a tetrahedral, the sulfur has 1, 2, 3 sulfur oxygen sigma bonds. It also has 1 sulfur oxygen pi bond as a result. So it has 3 of these and then only 1 of those. So that's part A, looking at SO3 minus 2. Part B looks at PF6 minus. And so if we look at phosphorus, we know that phosphorus can make 3 bonds, but it can also make 5 bonds. In expansion of his octet. In this case, we need to make 6 bonds. We have that PF6, and so that negative charge is going to allow sulfur to now make 6 bonds because we've given it an extra electron. And so now we can draw the structure. We have 6 groups, so we expect an octahedral geometry. With those fluorines. About the phosphorus. And so that is our structure. We would then have a negative charge on that structure. We're just kind of throwing that in the top right corner here. And so if we look at our phosphorus is D2sp3 hybridized. It's made 6 bonds, so it needs to use 6 orbitals, which it does with D2sp3 hybridization. And we find that we have all phosphorus fluorine bonds, all of them being sigma bonds, and there's actually 6 of them surrounding that central element. So that is part B. Part C looks at BRF3. It's an example that I've done in class. And so BRF3 actually would give us a structure that would have 3 fluorine-bromine bonds, but then would mean we would have 2 lone pairs of electrons left over on the bromine. And so what we end up with is that electronic geometry of trigonal bipyramidal to give us this type of structure. And if we were looking at the molecular name, this would be T-shaped. And so we have essentially, in this case, simply bromine-fluorine bonds. These are all sigma bonds. and we have 3 of those sigma bonds. The bromine atom, since it has 1, 2, 3, 4, 5 groups around it, that means the bromine is dsp3 hybridized in order to accommodate those 5 groups, which also gives rise to that trigonal bipyramidal electronic structure. So that's B and C. The last portion, part D, looks at HCN. HCN, if we put it together just following our octet rules, we should get a structure that looks like this, where we have a triple bond between the carbon and nitrogen and a single bond between the carbon and hydrogen. And so this is how this structure would actually look like. This is a linear structure. And so our carbon atom, as a result, is sp hybridized. It has 2 groups around it, a hydrogen and a nitrogen, and so it needs 2 orbitals to hybridize to have sigma bonds. And so we have 1 carbon-hydrogen sigma bond as a result. We also have 1 carbon-nitrogen sigma bond, 2, but then we also have 2 pi bonds between the carbon and the nitrogen. Each pi bond gives another level to the double bond, and then the final level to the triple bond. That is number 64.